All right, kiddies, welcome to our little video. I'm sorry I can't be with you in class today, but what we're going to talk about today is Coulombs Law, which is going to look at the forces that are occurring between two objects that accumulate charge. So we just did a set of labs where you were able to see some forces of attraction and repulsion between two charged objects. So today we're going to talk about and simply look at that force, and we're going to introduce a law that describes what's going on between charged objects known as Coulombs Law. So to get you guys all lathered up with what we're going to be doing today, I got a quick little video for you guys to enjoy. Whoa, boy. That's probably a perfect stop or spot to end. Here we go. Let's continue. All right, so like we saw with the cute little staticky kitty thing, so dang adorable, it's just ridiculous. But as we can see, that balloon doesn't normally stick to kitty cats, folks, okay? Balloons and cats normally don't get along as cute as cats are. So there is something obviously there that's making the balloon stick to the kitty cat. And again, like we talked about last time, it's all having to deal with charge. We have, obviously if there's attraction going on, we have two unlike charges. So you could have a negative charge, again, with a neutral object, could be a negative charge with a positive charge, or vice versa. So obviously one of those things is charging. And again, all this stuff, it goes back to the very beginning of our first intro lab that we did with charges with the hanging pith ball. Take, for example, when I bring a negatively charged rod near a pith ball, one of the things that we saw happen was that the negatively charged rod attracted, whether it was neutral or positive, but attracted a pith ball. All right, so if you think about the forces that are going on within this object here, within the pith ball itself, let's consider the forces. Now, at normal, when the pith ball hangs without the rod being brought near it, forces that are acting on it is obviously we have the force of gravity pulling it down and tension pulling it back up. But now once you bring this rod near the pith ball, all of a sudden those forces change. And you can see that obviously by the motion of the pith ball. You can also tell obviously by the rope that it's suspended by that it's at some sort of angle now. So if I were to ask you to draw a force diagram here, we would still have gravity acting straight downward. We would now have tension acting at an angle. And now, if this thing is still being suspended, all the forces are balanced. So think here, if we go back to forces, we have a component of tension to the right and a component up. So forces, we know that the up and down are balanced. So just thinking about this thing being suspended, if there's a force to the right caused by tension being at an angle, that must mean that there is a force going to the left. Okay? And if I were to ask what is the result or what is the cause of that force, what is actually making that happen, I'm assuming most of you would probably believe that that force is due to the rod itself. There's something about the presence of that negatively charged object that is causing that pith ball to go out of equilibrium and suspend at an angle. And that's exactly what we're going to talk about today. Today we're going to focus on this force, okay? All right, so this is going to introduce what we're going to talk about today, which is known as Coulombs Law. Coulombs Law describes what is called the electrostatic force, which I symbolize as F with a subscript of E. Okay, so again, it is a force. A force, going back to what we talked about first semester, is a push or a pull. So we're going back to things, again, measured in newtons. So this is a force. But what this force describes is what happens or the interaction between two, whether it be like or unlike charges. Okay, so this could be the force between a positive and a negative and a neutral, a positive and a neutral, and heck, it could be between like charges, such as positive, positive, and negative, negative. So this equation describes the force acting between any two objects that are experiencing a force dependent on charge. So let's take a look at the equation and see what we have. Okay, so going back to the previous slide with the pith ball, two things obviously we have is this force is a result of charges. So in this equation you will see Q1 and Q2. Okay, Q1 and Q2 are the two separate charges. So for example, if it is the rod and the pith ball, let's say that the rod is negatively charged, and since we're talking about charges, let's make this positive. Okay, the rod could be considered Q1, and the pith ball could be considered Q2. So it's an interaction between two charges. You will also see me a little bit later on, I may also label this as, let's say, capital Q and lowercase q. So I might distinguish it too as a uppercase and a lowercase, and we'll talk about that more as we get into what is the actual cause of this force. But we have the two Q's, so we have our two charges. Also notice that in the previous example, if you look at the labs we did, all it was is that I had to bring an object near. Okay, I didn't have to actually make contact. It wasn't a physical push. Or sorry, not a physical push, but there wasn't contact between the two objects. This goes back to introduced forces, that the electrostatic force is what's called a field force, meaning it acts at a distance. That these two experience this force when there is a distance separating them. So that is where we have the variable d in the denominator. This here represents the distance between the two charges. Okay? Now, in this equation, notice that the distance is being squared. This is known as an inverse square law, which means the inverse means that the distance is in the denominator. So as the distance, for example, gets bigger, means they get further apart. Inverse means that that force would get smaller. But because it's a square, as this distance gets bigger, the force actually decreases by a squared value. That's why it's called an inverse square. So for example, if I were to take and have the distance, okay, say I have the distance, that would result in a fourth of the force because we are taking that variable 2 and squaring it to become a 4. All right? So what we have is the two charges, Q1 and Q2. We have our distance. And lastly, we have this variable of K. Now, what is K? K is known as, I know I've got so many arrows going on here, but K is known as Coulombs constant. Okay? Coulomb's constant is exactly what it is. It is a constant. It was determined experimentally. Now, what is this value? This value is 9 times 10 to the 9th. Okay? So it's 9 times 10 to the 9th. I'm not going to necessarily worry about units, but if you really want to worry about it, it is newtons times meters squared over coulombs squared. Okay? The reason why it has those units is that if you were to plug this in, the thing that would be remaining, meters squared would cancel out here, coulomb squared would cancel out with those two, so the thing that would be left over is newtons. Okay? So this is a value that you need to make sure you write down, 9 times 10 to the 9th. Here's what I like to relate this to. Now, it's not the same, so don't get confused thinking that is exactly the same, but this is very similar to gravity, because remember, gravity is another one of those field forces. This is very similar to the variable g, that is about 10 newtons per kilogram if we were to think of units. Okay? Now, where I want you to understand the difference is, think of gravity. Now, again, I don't want you to compare these values as is, because it is a little bit different, but I do want you to compare the magnitude. 10 versus 9 times 10 to the 9th. This is 9 billion, this is 10. Okay, so there's a huge difference in the strength between this force and gravity, and it's all due to this constant. The constant kind of gives you a representation of how strong the force is. Okay, now I got a lot of stuff going on in this page, but what this equation again describes is that it describes the force between two charged objects. Okay? All right, so again, this is kind of what's going on. I just wanted to show you some pictures of here what's happening. So this force again goes between two charges. So here I would have Q1 and Q2. Those would be the charges I have here. Ignore the lowercase. It can be lowercase, it could be capital. Okay. D, labeled here as R. Let me change that for some of you that may get confused. Okay. D is simply the distance between it. And then our variable K again is down here is 9 times 10 to the 9th. Again, 9 billion Newton meters squared per Coulomb squared. That's that constant that's going to be there all the time. Okay? Now again, this force explains what happens between any charged objects. So when Q1 and Q2, I'm going to have you guys look at this force as a scalar. So we're really going to ignore plugging in positives and negatives. Okay? When you plug in Q1 and Q2, I just want you to think the value. But what I want you to understand is that sometimes both charges could be positive. Sometimes they could be both negative. When they're both the same, the good thing about this equation is that when you have two positives times each other and two negatives, that both of these result in a positive answer. Okay? Anytime you were to have a positive times a negative or a negative times a positive, these two would actually result in a negative. And I'll write F here because I want you to understand it's a force. So anytime if you were to plug in signs, you're actually going to get something that might be a little backwards in your heads. But a negative force here would actually represent repulsion. I'll just put rep. And here this would represent attraction. I'll just put that, okay? So instead of paying attention to signs, what I want you to understand is just Q1 and Q2 as a scalar, as just a value. So we're only going to look at the magnitude, and then we're going to worry about signs because it all goes down to the basic law that if we have like charges, they're going to repel. If we have unlike charges, they're going to attract. All right, so let's do some quick examples. So I have two charges separated by 3 centimeters. Object A has a charge of 6 microcoulombs, while object B has a charge of positive 3 microcoulombs. Now, the key thing here is you will see, and I mentioned this before, you are going to see, since we are dealing with charge, which is small, you're going to see micro, you're going to see nano, heck, you might even see milli. Remember that these, you jot this down, micro represents 10 to the negative 6. So when you see 6 microcoulombs, that is 6 times 10 to the negative 6 coulombs. Okay, when you see 3 microcoulombs, that's 3 times 10 to the negative 6 coulombs. So that's one thing you need to understand is that when you see those prefixes, you have to convert it to scientific notation. So micro, 10 to the negative 6, you might see nano, which is negative 9, and milli, which is negative 3. That's something you have to do. Otherwise, we are assuming it's a 6 coulomb charge if you were to just plug in 6. All right, so in this case, I want to know the force on object A. Okay? So if I were to draw a picture, I have object A here, which is positively charged, object B, which is also positively charged. Okay, I drew B a little bit smaller because I guess it doesn't really matter, but just the amount of charge, it's about half of what object A is. And they're separated by a distance of 3 centimeters. I don't like 3 centimeters, so I'm going to convert that and do 0.03 meters. Okay, and I want to know what's the force going on between them. So first of all, what type of force would we have? If they're two positive charges, that means it's going to be repulsive. So if I want to know the force on object A, I'm thinking, okay, how does B interact with A? Well, it's going to be a repulsion, so A would experience a force that goes that way. Now, at this point, I'm going to neglect anything related to gravity because I'm not giving you any mass. We're just worried about the electrostatic force. So to find the force on A, I'll just write FA. Okay, I'm just going to use the Coulombs Law equation that F is going to equal K Q1 Q2 over D squared. Now I'm just going to plug in my variables. Now when we do this, you're going to see some bigger numbers. So I have K, which is 9 times 10 to the 9th, Q1, which is 6 times 10 to the negative 6. B is 3 times 10 to the sorry, my little pen's going nuts here, 10 to the negative 6th. And all that is going to be divided by 0.03, which is the distance, but I got to make sure I square this. Okay? Now, key thing is punching this into your calculator. You are dealing with scientific notation, so when you punch these things in, you got to make sure that you use the power of 10 correctly. One thing to make sure to do is use parentheses, okay? And then pay attention to the square at the bottom. You're not just dividing by 0.03, but you're dividing by 0.03 squared. So why don't you punch that into a calculator and let's see what you get. Go ahead and do that. Ready, set, go. All right, once you punch that in, you should get a force of 180 newtons. So that means on our diagram here, this force is equal to 180 newtons. Okay, now, next question says, what is the force on object B? Okay, let me draw this in orange for you, but here's B. So I want to know, how does A interact on B? Well, we know that B applies a force of 180 newtons on A. I'm asking for what force does A apply back on B? Okay, now I know the charges are different, right? This one has a charge of 6, and this one has a charge of 3 microcoulombs. I'll put this in there so we don't get confused. Microcoulombs. But how do the forces act, or how do they interact? Well, we know that if they're both positive, this one is also going to be a force of repulsion. But the question is, how much force are we applying? How much force is A applying on B? Well, if you really think about it, I could go ahead and use the same equation, right? I could do K, Q1, Q2, and D squared. The only thing that would be different is 3 would go here and 6 would go here, but I would get the same answer. So this right here, I'm not going to punch it back in, but what you should do, and if you want to try it, go ahead, but you should have 180 newtons. Okay, all you're doing is switching the two charges in the equation. So what is this showing? This goes back to show that even at the subatomic level, even with electrostatic forces, that this shows Newton's third law, that the forces are equal and opposite. So that's kind of the other brilliant thing about this equation, is that it shows and proves Newton's third law even at the smallest level. All right, this is the last example I'll do with you guys, and then I'm going to have you guys try one on your own. So I want to know, how far apart are two electrons if they exert a force of repulsion of 1 Newton on each other? So key words here, we know the force, 1 Newton. Recognize variables there. I have 2 electrons. So if I were to draw this picture up here, I would have a negative charge and a negative charge, because electrons are the fundamental negative charges. What type of force would they apply? Well, I know that they would each experience a force of repulsion. Okay, so that would be a force of repulsion, and like we just saw in the previous example, those forces would be the same, but they act on different objects. So to calculate this force, I'm going to use the equation F equals K Q1 Q2 over D squared. Now we know K is a constant, 9 times 10 to the 9th. Our goal in this problem, folks, is to solve for, whoa Nelly, the distance. I don't like what I did there. That was just disgusting. Ah! There it is. I don't even know what I'm doing right now. I'm scribbling out everything. It's crazy. But I want to solve for the distance. I'm sorry, I'm going berserk right now. All right, so we know K is 9 times 10 to the 9th. All right? So I can punch that in. Q1 and Q2, if we're talking about 2 electrons, what is the charge on those 2 electrons? Well, there's a reason why we talked about that. Charge is all based on electrons, because it talks about the lack or excess of electrons. So I know that Q1 and Q2 are both going to be the fundamental charge, which is 1.6 times 10 to the negative 19th. So I'm going to punch that in for Q1 and Q2. Now, I could do a shorthand way, and I could write it as 1.6 times 10 to the negative 19th, and then I could square it, but that might confuse you, so we'll just keep it that. I want to know what is the distance, so if that's what I'm solving for, let's leave it in there, and then I want to find, I know the force is 1 Newton, okay? So my goal is to find the distance. Now I'll let you guys figure this one out algebraically, but your goal is to solve for D. It's in the denominator. So one thing you can do, taught you a little trick a while ago, is that you can just switch these. That the distance squared will equal, and then I can plug in all the rest. 9 times 10 to the ninth, 1.6 times 10 to the negative, oopsie daisies. Erase that for a second. 10 to the negative 19th. I'm going to shortcut. I'm just going to put squared, and it'll be all that divided by 1 Newton. And the last thing I'd have to do is obviously get rid of that square by square rooting, and I'd have to square root whatever I got there. So why don't you punch that into a calculator? Let's see what we get. And why don't you give it a shot? All right, and the answer you should get is 1.5 times 10 to the negative 14th meter. Remember, on your calculator, that E represents negative 14. Very small difference, but distance, but guess what, folks? Electrons are freaking small. So the distance between electrons are going to be so freaking small that we can't even see it. So if that answer doesn't make sense to you, really think about it. Negative 14, that's very close together. But at a subatomic level, very close together also means that you're so far apart. That's why it goes back to Metallica, folks. So close, no matter how far. All right, folks, I got one more example here for you. I want you guys to see if you can give this one a shot. So at this point, I want you to pause the video, okay? Give her an old pause. Try this one. I want you to find the electrostatic force between sodium, a positive sodium ion, and a negative chlorine ion, okay, that are separated by 0.5 millimeters. So give this one a good pause. See if you can give this one a whirl. Go ahead. Pause it. Pause the video. I'm not going to write it on here until you pause it. Okay, pause. All right, and here is the answer, folks. Here's what I had to figure out. It's kind of a little chemistry here, but when you have this plus sign, that means it's a positive ion, which means it has one extra electron. So that means the charge on this sodium atom, Q1 we'll call it, is going to be equivalent to the charge of having one electron. So in my equation, Q1 I did as 1.6 times 10 to the negative 19th. Similarly, this one, chlorine, having a minus means that it's missing one electron. Okay, so that means it's kind of the same thing. This would be Q2, which would be the charge of one electron as well. The only difference between these is that Q2 is going to be negative, Q1 is going to be positive. So in my equation, I kind of have that. Think of this charge here as Q1, 1.6. This is negative, Q2 is that. Now in the equation, I didn't label it as negative because I know, just knowing from it's a positive and negative, that it's going to be an attractive force. So I only want to plug in the magnitude of those charges, and I don't care about the actual sign on those. But when you punch everything in, you should get 9.2 times 10 to the negative 22nd. Not a big force again, but we are talking about things that are very small. But we do have that force of attraction going on. So that's a quick little run through on Coulombs Law and finding the electrostatic force. Your next goal, after watching this video, took good notes, you are working on the Coulombs Law worksheet. Got any questions, shoot me an email. Otherwise, we'll see you next time and catch you on the flip side, folks. Take it easy. All right, peace. I'm out of here.